Good afternoon, everyone, and welcome back to the AP Physics 2 pretest review. Today, we're starting day 1 of circuits. So buckle up, it's going to be a busy day. We're starting with conservation of charge, resistivity, and resistance, dipping a little bit into Ohm's law. But first, let's run through today's agenda. We're going to start with a lesson overview and discuss how the lesson's going to shape up and what we're going to be working on. Then we'll do our daily warm-up. We'll pick up where we left off yesterday with the AP practice problem and get some warm-up to get your brains moving. We'll discuss what you need to know to be successful on questions involving resistance and resistivity. Then we'll do some guided practice, some sample questions from the question bank, some former AP physics problems. Then we'll do a debrief and summary, talk through what we worked on and make sure you learned all the bits and pieces. Then we'll leave you with an AP exam practice problem that we'll start tomorrow's lesson with. So that's the rundown. Here we go. I am Joe Mancino. I teach at Glastonbury High School in Glastonbury, Connecticut.
And I'm Brendan Eaton. I teach at Reedy High School in Frisco, Texas. And as usual, we're going to go ahead and start with a roadmap of the rest of the review sessions that we have left. As you see with the blue arrow, this is where you are currently located. We are starting circuits today. We have 4 lessons of circuits, and then we move into magnetism, which is fantastic. Can't wait for magnetism. All right, so as far as today's lesson is concerned, we'll start by talking about current, specifically what is current, and we'll discuss the relationship between rate and speed and how that applies to current.
And then we'll discuss potential difference, the difference in electric potential, how different arrangements of batteries yield a different potential difference, and really what potential difference means anyway.
After potential difference, we'll talk about resistance and how resistance and length are related, resistance and thickness are related, and resistance and the material itself, how that affects the resistance.
And then we'll talk about Ohm's law, which is just Ohm's law.
There's a lot there. The skills that we'll use today are using representations and models. We will be making claims and predictions about natural phenomena based on scientific theories and models. We'll be connecting concepts in and across domains to generalize or extrapolate. And we will also be applying mathematical routines as usual.
So here comes a warm-up. Here's where we left off yesterday. We had 2 charges, and you had a drawing of the equipotential lines around those charges. You knew that one of the lines was at 50 volts, and that the iso lines are separated by 10 volts each. So your job was to figure out the voltage, the electric potential at point A and at point B. So the electric potential at point A, we're told that the iso lines are 10 volts apart. So the potential at point A is 60 volts. The potential at point B is 80 volts. Now we know that's the case because we're told that the sphere located at point Y is positively charged. So that means it is a higher potential. Points near point Y are at higher potential. So point B must be at a higher potential than point A. It's separated by 2 iso lines, so it's 2 10-volt jumps higher. All right, how do the magnitude of the signs of the charges compare? And explain why. Well, Y clearly has more potential than X. The nearest potential of the same value is farther away from Y. So points even closer to Y would have even more closely spaced equipotentials. And at some point, they just become silly to draw. We weren't going to do that. So X and Y must have the same sign because there is no point between them where the potential is 0. There is no point between 2 charges of the same sign, if they're the only things around, where the potential is 0. Potential at any point is the sum of the individual potentials. And if both charges have positive potential, there's no point where a positive potential and a positive potential add up to 0. All right, and then there's this question about mass versus electrostatic attraction and repulsion. The sphere's masses are in the same ratio as the magnitude of their charge. Kind of clued you into that yesterday. The isolines of gravitational potential have the same shapes as the isolines shown. Explain why they have similar shapes. Well, the way that we have it here is kind of in teacher speak. If we were to bring in a sphere of the same sign as those charges, it would be repelled by those charges. If we were to bring in a sphere of similar sign, it would be attracted to those charges, but the strength of that force would vary in proportion with the closeness of the isolines. So regardless of whether we're drawing gravitational isolines or electrostatic isolines, the strength of the force, the magnitude of the force, depends on the closeness of the isolines. Okay, so there were 3 points labeled A, B, and C, and the potentials at those points are VA, VB, and VC. A proton is released from rest at point B. And our job was to describe one similarity and one difference between the forces exerted on that proton. Now, that's a long setup to say, how is electrostatics like gravity, and how is it not like gravity? Well, electrostatics is like gravity in that they are both inverse square laws. That was one argument that you could make. Or you could make the argument that both depend on one property times the same property in two different objects. You could also, as a difference, bring up the fact that gravity is only ever attractive, whereas electrostatics can be both attractive and repulsive. You could also bring up the idea that they have those different coefficients. Electrostatic attraction and repulsion has 9 times 10 to the 9, a coefficient of 9 billion, whereas the universal gravitation constant is much smaller, 6.67 times 10 to the negative 11. That's a factor of 10 to the 20 difference, give or take. All right, sometime later after being released, the proton has moved through a potential difference of 20 volts. Determine the change in the potential energy and express your answer symbolically. So the change in electric potential energy is charge times the voltage, the change in potential. Delta V is voltage. Well, delta V just is a comparison of the potential at 2 points, so VA minus VB. And then finally, as it is moved through that 20-volt difference, our job was to determine the work done on the charge. Now, the work done on the charge, we talked about in our lesson from Monday. The work done is the magnitude of the charge times the average electric field times the distance over which it is moved. If that seems unfamiliar, double check that video from Monday. It is another way to express Q delta V. All right, last piece. Two students are arguing. Student 1 says, if the system is just the proton and the sphere, then the increase in kinetic energy, the increase in the proton's kinetic energy is due to a change in the system potential energy as the proton moves through that 20-volt potential difference. Student 2 says, if the system is defined as just the proton, the kinetic energy of the proton increases because positive work is done. Well, this doesn't happen often, but both students are correct. The definition of the work energy theorem, the definition of conservation of energy, depends a lot on how you define the system. If the system is the proton and the spheres, then the total mechanical energy, the total energy of the system is conserved. Electric potential energy is transitioned into kinetic energy. Or if we're just looking at the proton, external work is done on the proton by an external force. But both of those definitions are internally consistent, depending on how you define the system. Definitely pay attention to that. The idea of systems and energy and conservation laws is core to the understanding of AP Physics 2. If you think you have a really good handle on systems in which energy is conserved, ways that momentum is conserved, then you're going to do brilliantly on the AP Physics exam.
All right, thank you, Mr. Mancino. Let's go through what you need to know to be successful on this year's AP Physics 2 exam. First off, current is the rate at which charge flows. You've probably heard that before, but we're going to go into more detail about that today. We will also discuss how electrons vibrate quickly and drift slowly, and the unit of current is ampere. We'll also dive into potential difference and current being the rate at which charge flows again. Notice that we said that
Wait
twice.
a minute. Yeah, I think something happened here.
It's okay.
That's awfully strange. When we talk about current, we will discuss how adding batteries in series versus adding them in parallel produces a different potential difference, and we'll talk about what the effect of potential difference really is.
There
My
you go.
apologies.
No worries, no worries. So with resistance, we'll be talking about how longer resistors have more resistance, wider resistors have less resistance, how the material itself is intrinsic and affects the resistance, and the series and parallel combinations of resistors. We'll kind of review that. There's going to be more on that anyway, so today is just kind of a primer on that again. And ohmic versus non-ohmic resistors, what does that mean? What does it look like in graphing relationships, so on and so forth. And last but not least is Ohm's law. So I is V over R. And we will still talk more graphing on Ohm's law in this presentation as well. And what does it look like? So we'll start with electric current. So electric current is just the organized motion of electric charge. It's the rate at which charge flows. So notice that you've heard the term rate so many times in AP Physics 1 and AP Physics 2. And when you see rate, you know that that has something to do with per unit time. So I know that current is the organized motion of electric charge, and specifically we think of it as flow rate of electrons, but we're talking about how much charge passes a given point inside of a circuit every second. And so what does that look like on your formula chart? So if you pulled out the AP Physics 2 formula chart, you would see I is equal to change in Q over change in time. So again, what that means is how many coulombs of charge pass a given point every second. It's really a flow rate of charge. That's all it is.
The unit of current is the ampere. An ampere is 1 coulomb per second. I should have capitalized coulomb. Sorry, coulomb. It doesn't sound like much. 1 amp of current doesn't sound like a lot, but 1 amp of current is 6.24 times 10 to the 18 electrons per second. I don't even know what that's called. It's bigger than a billion, bigger than a trillion, bigger than a quadrillion. I don't even know. It's the next one. That's a lot. Electrons vibrate with thermal motion. That's about 1,000,000 meters per second. So let's back up. We've got this many electrons to make even 1 amp of current vibrating that fast, 1,000,000 meters per second. But the electrons that flow in an actual current, it's not the random thermal motion that does it. It's the drift speed. The drift speed of electrons, the gradual bumping, bumbling, slow drift because of an imposed electric field is very slow, about 1 foot per hour. That random thermal motion of electrons that we talked about, particles having thermal motion when we talked about thermodynamics days ago, random thermal motion adds up to 0 because it's random. For every particle moving left, there's one moving right. For every particle moving forward, there's one moving backwards. The thermal motion of electrons adds up to 0. If you go to the hardware store and buy a roll of wire, the average velocity of the electrons in that bundle of wire is just 0, even though they have temperature. The average speed of the electrons in that wire is really fast, about 1,000,000 meters per second. But once you run current through that wire, the drift speed of the electrons in that wire, the speed of the current, the speed of the flow responsible for bringing electrical energy around the circuit, that's about 1 foot per hour. And we'll discuss a little bit more about that tomorrow, about why it is that charge starts to flow the moment, charge flows everywhere the moment charge flows anywhere. And even though those charges are moving slowly, a large number of them are moving. It's a very large number. So I looked at the current rating on a flashlight and it said 20 milliamps. 20 milliamps is 0.02 amperes, 0.02 amps. So 0.02 coulombs per second. And that doesn't sound like a lot. I can definitely touch a flashlight and not worry about the amount of current. 0.02 amps is not a lot of current, but it's a lot of electrons per second. That's 124 quadrillion electrons per second. And that's a lot, even though it's not a big number for current. Current isn't about how fast electrons flow. It's about how many flow per second.
So what we're trying to say is if you buy a power cord or an extension cord from the store, which is made of wire, they carry current. They are electrically neutral until you apply some sort of potential difference to that. And even though those electrons are moving through the wires, there are no actual extra electrons inside of a conductor when it's carrying current. You're simply, I like to describe it as popping one electron in and one electron is basically coming back out the other side. It doesn't have extra electrons because once you unplug that power cord from the wall, it no longer has any charge in terms of what you normally think. You can take that power cord out and touch the prongs and nothing's going to happen. So that's something that you need to know is that wires are electrically neutral. They don't have extra electrons.
Yep, wires are always considered uncharged, even though we use the word charge to mean my phone is charging. Well, that's different. Conversationally, one of the biggest problems that I encountered as a physics student as I learned this was I had conversational definitions of work and energy and power and voltage and electricity and flow and current and resistance and all of those words. I thought I knew what they meant. Your struggle as an AP Physics 2 student right now is nailing down very firmly the actual scientific precise definitions of these terms. And it certainly can be very challenging, especially as we use words that have colloquial meaning, like charge and energy and electricity. So one of the hardest words I struggle with even now is the conversational usage of the word voltage and the precise usage of the word voltage. Voltage is shorthand for the difference in electric potential. It is literally the potential at one point minus the potential at another point. But when you buy a battery, you don't say, I need a battery with a difference in electric potential between its terminals equal to 1.5 volts. That is not what you say. You say, what voltage battery do I need? 1.5 volts. But what that really means is we are subtracting the electric potential at one end of the battery from the electric potential at the other end of the battery. It's just subtraction. Now, here, with one battery arranged like this, if you bought a AAA battery off the shelf at a store, it's 1.5 volts. If you arrange them like this, it's double the voltage. It's 3 volts. The charge moves through one battery. An electron would move from the positive terminal to the negative terminal and gain 1.5 volts of 1.5 electron volts of potential energy, and then move through the next battery, and that single electron would gain another additional 1.5 electron volts of potential energy. every charge that goes through these batteries, every coulomb of charge, every bundle of charge gets double the amount of energy because they go through the batteries twice. But batteries do not make electrons. Batteries don't make charge. The positive end of the battery is pulling on electrons, and the negative end of the battery is pushing them out. That's what's really going on. There's an oxidation or reduction reaction happening inside the battery. If you happen to have a chemistry background, that makes a lot of sense to you. If not, there's chemistry happening. The positive end of the battery pulls electrons. The negative end of the battery pushes electrons out. But batteries don't make charge. They give charge energy, but they don't make charge in exactly the same way that fans don't make air. Fans grab air from behind the fan. They grab slow air from behind the fan, and they push out fast air in front of the fan. They grab air with low kinetic energy, and they push out air with high kinetic energy. But fans don't create the air. Something that the fan is doing gives the air energy, but fans don't make air in exactly the same way that batteries do not make electric charge. All righty. Now, I don't know if you guys maybe did this experiment in your classroom. It's one that I've always done with my students. If any of my current students are watching this, well, you know where this is going. Blowing air through one straw is kind of easy. If you take one straw and pressurize your lungs and blow on the straw, there is flow through that straw. Blowing through two straws arranged like this is about twice as hard. You get out about half the flow. It takes somewhere near twice as long to fully empty your lungs through these two straws. Adding a third straw or fourth straw or fifth straw is increasingly difficult and looks increasingly ridiculous. And the more straws that you add, one after the other, it becomes even more difficult to blow air through the straws. With the same pressure difference between the inside of your lungs and the outside air, adding more straws like that makes it more difficult to get air to flow, and it slows the flow of air. And so in my class, after we do the straw example, we use a multimeter and measure the resistance of a material as a function of its length. So we take strips of resistive material and measure for every centimeter of length what its resistance is. And I'd like you to pay attention to the blue line on the next slide, just the top line. We did it with a few different types of material that we'll discuss later, but the blue line is the one you can pay attention to. You'll see that we used varying lengths between 0 and 10 centimeters, and we measured resistance between 0 kiloohms and about 20 kiloohms. So longer and longer and longer strips of this material had more and more resistance. Now, being clever scientists, my students said, that looks like a linear relationship, Mr. Mancino. So we mapped it to a linear fit, and it was a really good fit. It was a linear relationship. So resistance is linear with length. The longer a resistor is, the more resistance it has. But then we do the experiment with the straws. Again, blowing through one straw is kind of easy, but blowing through two straws that are next to each other is even easier. It's half as difficult. You can empty your lungs twice as fast. With three straws, it's even easier. Now, what you'll notice is one straw has its own cross-sectional area. Two straws has double the cross-sectional area. Three straws has 3 times the cross-sectional area. And that's what those different colors mean. So here's the rest of the graph. We did one strip of conductive material, and then we measured the resistance of 2 strips sandwiched together. They were thin strips of material, but you'll notice that red line, that 2 strips of material, has about half the electrical resistance of the blue line, all the way down to the green line, which has about 1/4 the resistance of the blue line. So the thicker the material is, the less resistance it has. Or the wider the straw you're blowing through, the less resistive it is for airflow.
So what this means is electrons are able to move more freely in some materials than in others. It's almost like it's a property of the substance itself. So a material's resistivity, notice that that's different than resistance. That measures how difficult it is for electrons to flow. So something that has a large resistivity, it's more difficult for electrons to flow. Something with a very small resistivity, electrons flow fairly easily through that material. So the symbol for resistivity is the Greek letter rho, which is, yes, I know, the same symbol as density. But in terms of electricity, when we're talking electricity, when you see rho, you need to know that that is resistivity. And again, that's a property of that material itself. So each different material, each different element has a different resistivity that's intrinsic to that substance. Now, we also know that an object's resistance depends on its length, its cross-sectional area, and its resistivity as given by Mr. Mancino's experiments that his students did in class. So we noticed that as the length increased, we got more resistance, and as the cross-sectional area increased, we got less resistance out of those materials. So how does that play into an equation? This is what's on your formula chart. You see a big R is equal to rho L over A. Now, big R stands for resistance. Rho, we just said, was resistivity, which is something that you can look up in a table, or maybe you're given that quantity inside of the problem, or we're going to talk about how you can graph to find that resistivity. Now, the L on top is for the length of the wires. Typically, what we talk about is the length of the wire, and that's all over the cross-sectional area. And just a fast reminder, the cross-sectional area of a wire, wires are typically round, so a cross-sectional area is just a circle. And what's the area of a circle? That turns into pi r squared on bottom. 9 times out of 10, that's what you're going to be using. But the question that we're going to leave you with today is actually a rectangular prism. So think about, before we get there, think about how you'd find a cross-sectional area of a rectangular prism.
So I want to say thank you, Mr. Eaton, for discussing some of the functional dependence of the terms in that equation. These students are going to have to be doing that on the exam in May. You'll be given some sort of equation and asked to interpret what would happen if some of those variables changed. Well, if the values in the numerator change, that means that the value is getting bigger. If terms in the denominator increase, the value of the fraction is getting smaller. So increasing a numerator generally means that the value of what you're measuring is increasing. Increasing a denominator means decreasing the value. So in this equation, decreasing cross-sectional area increases resistance. You will also be expected to read and interpret a circuit diagram. So I do want to just take a moment. I'm sure that you know about circuit diagrams, but this is how we diagram a resistor. And a resistor is anything that converts electric potential energy into another form of energy. So it could be a toaster, it could be a jacuzzi, it could be a flashlight. They're all drawn the same way.
And anything that has the effect of making a longer resistor increases the resistance. So if you make the resistor physically longer, that's going to increase the resistance. All right, so if you have this one resistor, how would you increase the resistance? So we just said if you can make it longer. What if I put a second resistor right next to it in series? In terms of R naught, what's that new resistance? Well, I have to go through 2 resistors if I'm imagining traveling from the left-hand side to the right-hand side. So that turns into 2 R naught. It's twice the amount of resistance. I've effectively made R naught 2 times longer. Well, what happens if you stack 3 of them together, end to end? And again, this is a series circuit, a series combination of resistors. There's 3 R naughts all in line. And imagine traveling from the left side to the right side. You have to go through 3 of them. So the total resistance in that case is 3 R naught.
Just like having to blow through 3 straws in a row. So we discuss adding up resistance and different ways of combining resistors. So in this example, we've got one resistor with a resistance of 2 R naught, another resistor with a resistance of 1 R naught, and that adds up to 3 R naught. Adding up resistors one after the other or in series is just a matter of summing the resistances. It's effectively like increasing their length. But anything that has the effect of making a resistor wider decreases the resistance. For example, here's that same resistor with resistance R naught. But what if we had two of them arranged what's called in parallel so that current can go through one or the other? In series, current goes through one and then the other, but in parallel, current has the choice of one or the other. When those resistors are arranged in parallel, it's half the resistance. Now, there is a way to calculate that. You will not have to calculate it on the AP Physics 2 exam. You may be asked to provide or select a symbolic representation of it. So here are 3 resistors arranged in parallel, R1, R2, and R3. And the way that we find the equivalent resistance, what is the resistance of this network of resistors, is 1 over the first one plus 1 over the second one plus 1 over the third one, and then find the inverse. All right, so the as we discussed a little earlier, you can cause more or less potential difference, more or less voltage, either by adding batteries in series one after the other, or using a variable voltage source. If you have one of those in your classroom, you might be familiar with that tool. It's got a little dial, you choose the voltage. What you, I'm sure, found out at some point in your AP Physics experience is that adding more batteries in series or cranking up the dial on a variable voltage source causes more resistance. Sorry, causes more current. The more current there is, the more current you want, the more voltage you need. The more you dial up the voltage, the more current you get. Likewise, I assume that at some point in your physics background, you varied the amount of resistance that current was flowing through with a constant amount of potential difference. So for the same potential difference, increasing resistance decreases current. Like blowing through more straws decreases the speed at which your air flows.
All right, and this is super familiar to you, I'm sure. This is Ohm's law as found on your formula chart, which is current is equal to potential difference over the resistance. And you can rearrange this equation in just about any fashion that you need to solve for a particular variable. And again, like we've stated several times, you're not going to need to do any math per se, but you need to be able to talk about this equation and say, if you change one variable or the other, how does that affect the current, or how does that affect the voltage, or how does that affect the resistance? So if I look at the format that we have it on the screen, if I increased the potential difference, delta V, that should have a direct relationship on current. So if I doubled delta V, that should double the current if I kept resistance constant. So what happens if you keep delta V constant and you doubled R? What would happen to the current? Well, that's going to make the current half as much. So there's an inverse relationship there. So things that are following Ohm's law are considered to be ohmic. So we typically talk about resistors and say this material has a particular resistance and it's inside of a circuit. It is ohmic if it follows Ohm's law. So if your graph turns out to be linear of V versus I, or I versus V, doesn't matter. As long as that graph is linear, you should have an ohmic resistor. And conversely to that, if you have a non-ohmic resistor, that means you have a non-linear line on that same type of graph. Now, ohmic also applies to the following Ohm's law with no change in temperature. We don't care about the temperature whatsoever in that case. So, Mr. Mancino, I think this is you.
Yes, that is the graph that would show an ohmic resistor. So for an ohmic resistor, increasing the potential difference, increasing the voltage, that means more current. Now, the same is true of a non-ohmic resistor. More potential difference means more current, but not necessarily linear. So resistors are ohmic if the relationship between potential difference and current is linear. If no potential difference causes no current, and if the same ratio of changes in potential difference causes the same ratio of changes in current. Doubling one doubles the other. So here is a sample question. A student was given 5 wires of the same length and the same diameter and the same material. Oops. 5 wires, same length and same diameter. The student connects the wires to the same battery one by one and measures the current through each wire. The table above shows the data collected. Now, which of the following can be concluded from the data? I didn't mean to say the same material. So we could either say, are the wires ohmic? Well, they're connected to the same potential difference, or the same battery one by one, and I see different currents. So if it's the same potential difference and different currents, well, ohmic is probably not a great choice. C says, the resistance of the wires depends on their size and shape. Well, all of these wires are the same size and shape, so we couldn't make any conclusions about that from the data. D says something about the battery having internal resistance, but we don't have enough data here to even talk about that. So yeah, it is B. The wires are made of different material. They're made of different material. We know that for sure, because the only thing that could be changing in that resistance relationship is that rho term, that resistivity term. When it comes to circuits, material is a stand-in for a conversation about resistivity. Now, when we get a battery at the store, yeah, you might say, I'm looking for a 6-volt lantern battery. It's got to have a voltage of 6 volts. And you'd be right conversationally, but what you really mean is the EMF is 6 volts. EMF gets the symbol E, and that's the printed voltage on the side of the battery. But when a battery is actually being used, when current is actually flowing through a battery, if you were to test the voltage between its terminals and actually measure it, what you actually measure isn't the printed EMF of the battery. An actual physical battery has a small amount of resistance called its internal resistance. Now, it's not that there's really a resistor inside the battery. I don't want you to think that. That's not what this diagram means. It just means that in the chemistry of the battery, something is happening that's using electric potential energy to do something to the battery. If you feel a battery, it gets hot. It slows the flow of current for one reason or another. Inside of a battery, it's like there's a small internal resistance, like an R internal. So when you use a battery, you don't get E, you get the battery's terminal voltage, and that's that term on the bottom left. Terminal voltage is the printed EMF minus a tiny bit of IR, a tiny V equals IR that's missing. Now, the more current you try to run through a battery, the more different the terminal voltage will be from the EMF of the battery. And as a battery gets older, its internal resistance goes up. The terminal voltage of a battery depends on the internal resistance and the current. If you're not running current through a battery, even if it's an old battery, you'll still measure the full EMF of the battery. All right. So can you rank these from least resistance to most resistance? All of these are the same material, but these resistors vary in length and cross-sectional area. So which one do you think has the least resistance? Well, from the straw example, I know that shorter resistors should have less resistance. So I think the shortest resistor here is Y. And I know that wider resistors should have less resistance. Y and X are the same length. So I think that the least resistance is Y. And somewhere in the middle is X, and the most resistance, that long, narrow resistor, that's Z. Well, if these were connected in a circuit, which one would have the least amount of current through it? Now, they would all have the same potential difference. Those resistors are arranged, as we say, in parallel. The potential difference is the same between the wires on the left and the wires on the right, regardless of whatever path a charge takes through them. So the least current would be running through wire Z, and wire Y would have the most current.
All right, and here's your guided practice for today. We're dialing it back to 3 questions this time. The first and the second are about resistivity, and the third is about combining resistors, just to give you a little bit of practice. All right, here's your first question about resistivity. A wire of length L and radius R, small r, has a resistance of big R. What is the resistance of a second wire made from the exact same material that has a length that's half as long and a radius that is half as much? So you've got 5 choices here, and I'm just going to dive into the resistivity equation. I know that R is equal to rho L over A, and since the materials are the same, the resistivity is the same. That's intrinsic to the material itself. So really, I can take rho out of the equation because I'm only looking for a proportion here. So resistance is essentially L over A in this case, which we talked about earlier. The cross-sectional area of a wire is going to be pi r squared. So if L and R are both half as much, notice that's what L over 2 and R over 2 are, I can set that into my proportion that I just designed to be 1/2 over 1/2 squared. Because we know the radius is 1/2, but it's still squared because of the cross-sectional area formula. So that gives me a proportion of 4 over 2, which gives me an answer of 2R. So pretty easy, pretty straightforward. And like we've said throughout this series, you don't really need to worry too much about actual calculations. So the resistance increased by a factor of 2. So what? Big deal. Here's what you should expect to see. How could you decrease the resistance by a factor of 2 instead? So maybe they'll give you the information beforehand and say, okay, well, the student now wants to decrease that resistance by a factor of 2. So looking at your R is equal to rho L over A formula, how would you instead increase by a factor of 2 just by changing one of the variables that you see in your equation? So if I want to decrease my resistance by a factor of 2, I could I could increase the radius. Notice that radius is on the bottom of that fraction. So if you increase radius, it decreases resistance. But I could also decrease the length, and that would also decrease the resistance. That's the type of thinking and the process that we want you to be familiar with in just looking at an equation. It's not about making the calculations. It's about discussing that equation and saying how each of those variables contributes to the overall resistance of the material. All right, here's your second question. It's got a lot of words to it, and that's okay. An engineer has 4 wires made of the same material, same resistivity, and wants to determine the material's resistivity. Engineer measures the length and the cross-sectional area of each wire, applies a potential difference across each wire, and measures the current to estimate the resistivity on the material using only the slope of a graph of the data. What should be graphed as a function of L over A? So we're asking you, what would you graph versus L over A? So what are you trying to put on the y-axis so that the slope represents the resistivity? So I've broken down just a brief little process here. It says the engineer only knows the current, I, and potential difference, V. They don't know R. So to get R, you need to graph V over I versus L over A. So this the V over I is actually equal to R because of Ohm's law. So you could go through and take that data and crunch it down and say, okay, V over I is R, or you could just graph V over I versus L over A. So using R is equal to rho L over A, we know that the slope should represent, if you're graphing R versus L over A, the slope is the resistivity rho.
And that is a great question for preparing for the test in May. You might be asked what quantities you would graph if you wanted to determine something from the slope of that graph. And knowing how to pull that out of an equation is a very important skill, both on the AP Physics exam and in physics in general, giving meaning to an equation and analyzing what that meaning would look like on a graph.
Perfect. All right, so here's your last question. You have a little circuit diagram. I see 2 points, X and Y, and there's 3 resistors in between X and Y, but they're not necessarily in a fashion that's super easy to understand. So I know that this is still a struggling point for several of my students when you see just a section of a larger circuit, and I want to know the effective resistance from point X to point Y. So if you're supposed to find the total resistance, the electrical resistance from X and Y, what I typically say is go ahead and draw that diagram and show where you can start putting resistors together. And I like to hone into the easy ones first. So notice that the 1 and the 3 ohm resistor are in series with each other. And if they're in series, I know I just have to add them up. That's all you do. That's 2 straws together. I know it's more resistance, so the number should be larger than any of those 2 put together. So I didn't show it on the screen, but I do like to redraw that diagram with a 4 ohm on the top and a 2 ohm on the bottom. So that bottom resistor then is in parallel with that upper branch. So in order to find the effective resistance, you would take 1 over the bottom resistor plus 1 over the top resistance. And I think I made a mistake in the math on this slide, and that's okay. But that should say 1 over 2 ohms plus 1 over 4 ohms, and then take the inverse, and your number should be a little bit smaller than 1.33 ohms. So that's a mistake on my part, and I apologize.
These things happen.
It's
so here comes your debrief and summary. Here's what we were hoping that you learned today. Current is the rate at which charges flow. That resistance depends on resistivity, length, and cross-sectional area, and that resistivity depends on the material. Resistivity is a material property, resistance is an object property. And that ohmic resistors follow Ohm's law, that current is proportional to potential difference. That there are 2 rules for combining resistors. There's the one after the other rule, and then there's the one or the other rule.
And can you answer these questions? What does a battery actually do? And how can you change the resistance of a material? Let's say I just give you a
That
random
sounds like a
material.
trick question. The resistance of a material.
That's not a trick question. It's a question that gets you thinking. And do you know what the difference between EMF and terminal voltage is? And why is there a difference between the two?
Big questions. Here comes your AP exam practice. Not a lot of pages today, so that's good news. Grab a screenshot of this one. We're designing a lab to determine the resistivity of a conductive material using a graph. As you prepare for this, as you think about this, definitely focus in on how you would graph it. Grab your screenshots. And this is a rectangular rod of that material, but its dimensions are not known. Could you sketch some data that would help us determine the resistivity of that material? Okay, thank you so much for watching. As we begin circuits, we have only 1 unit left to go. We are 1 day closer to the exam with 1 day of review behind us. Thank you so much, everybody.
Thanks again. We'll see you tomorrow.